In this video, we're going to talk a little bit more about linked lists. So this, I've got on the screen here the PowerPoint from the book, just because there's some graphs and stuff that I think will be useful to have. Okay. So we talked before about the linked list in general, what the operations of the linked list look like, and all the different things that go into that. Okay. So this time, the next thing that the book talks about, which is what we're going to be working with, is creating a linked list as an abstract data type. Okay. So there are a couple of reasons for this. The first thing is that they're going to want to differentiate between an ordered list, so that's always in sorted format, and an unordered list, which is a random order. Okay. So they want to do that by creating an overall abstract data type for the linked list that then can get specialized into unordered and unordered. Okay. And then as part of that, they're also going to use a templated class, which means that you'll be able to have a list of integers or a list of if you've created circle objects, you can create an integer of circle objects or an integer of whatever, or sorry, a list of whatever you have. So a list of whatever data type. Remember with the templates that you have a variable that refers to the data type. So you can write the same function for any data type that you want. Okay. So this abstract data type that we're going to be creating will have some basic operations. Okay. So again, this is different from our approach before with linked list in that we're going to create a linked list class that has these functions built in. So we'll be dealing with, we don't have to pass the list along. These are functions that the list can do. Be a little bit different, okay? But the basic operations we're going to have is being able to initialize the list, to return whether or not the list is empty, print the list, find the length of the list, destroy the list. We haven't talked much about the ramifications of creating these nodes. We're going to need to release that memory, like when we talked about the new keyword and the delete keyword. So the dynamic memory, these linked lists that we created or that we create are dynamic memory objects. So we have to clear them out, or at least we should. Okay. We'll be able to retrieve the info, and they're keeping track of the first or last node. So the last node is optional. You don't have to do that. I mean, you can certainly just keep the head or the root or whatever you want to call it to be able to track your list. But in this case, you're doing one at the first and also one at the last, and also to be able to search the list for some item. Okay. So other options we'll be able to insert an item into a list. Okay. We'll be able to delete an item from the list and to make a copy of the linked list. Okay. So linked lists are certainly big enough structures that we should revisit the idea of deep and shallow copying. Remember, if you do a shallow copy, it's also known as aliasing. You're just giving two names to the same list. Okay. And I'm not a big fan of such a thing. Okay. A deep copy makes a separate copy of all of the data in memory. Okay, so you see why it becomes optional, because it can be a very memory intensive operation. But if you need a copy, you need a real copy, it seems to me. Okay, so again, as I'd said, there'll be two types of lists we're going to be talking about: sorted and unsorted. Okay, so a lot of the basic operations are going to be the same. Okay, so things such as doing a copy is not going to matter. Doing a is it empty or not? That's not going to matter. Okay, but there are some things that will be different. Okay, so in particular, searching. Okay, so if we know that the list is sorted, we can do a binary search. Okay, where you can try to, or that's not correct, that we can't do a binary search. Scratch that, because we can't do indexing. But we can if we're searching, for example, for an integer 20. Okay, and we're going to have to start at the first and go forward. Okay, once we see a value greater than 20, we can stop, because we know any value of 20 would be before that. Okay, well, we're with an unordered list, the 20 could appear anywhere. Okay, also the insert. Clearly, if you're going to insert something into an unordered list, you just throw it at the end or throw it at the beginning, doesn't matter. Where on an ordered list, you have to find the right place to put it. Okay, the remove could be slightly different. Okay, so these are the things that we're going to to have to change when we specialize from a linked list into a sorted or unsorted. Okay, so we're going to have the abstract class will implement the basic operations. Okay, and then the derived classes, the unordered list, linked list, and ordered linked list will implement those changes. Okay, so for the unordered linked list, we can insert a new item either way. So we can either do the build list forward or the build list backwards. Okay, so we're going to have an insert and an insert last, and we'll have 2 pointers on that. Okay, for the unordered list. Okay, so let's see what else that there is to talk about this. I'm not sure. So this is an example again of using the templated features here. So our nodes are going to have this template class type. Okay, and the struct node type with the type info. Again, type will be int, it will be whatever. We use it. So if we're using integers, we would say node type angle bracket int angle bracket link, okay, rather than just node type as we've been using before. Okay. So let's see what else we've got here. There's an iterator. We haven't talked about iterators much, but the iterator, the linked list iterator here is going to be an object that will allow us to move through or traverse the linked list starting at the first node. Okay, so the operators we're going to use for this is the plus to increment, and then the asterisk to dereference. Okay, so the iterator, linked list iterator, I've already placed that out there. The class one, it's in the /tmp file. Okay, so you can use that as well. Here's the UML diagram for the iterator. Okay, you see that it has the dereferencing, it has the increment, it has equality and not equal, basically, are the operators we're going to have. Okay, so and then here's going to be our linked list type. So again, this is already out there in the /tmp file. We're going to be building from this. Okay, so this shows you, again, we have the name at the top, we have the data, okay, in the middle, and then we're going to have the operators or the methods or the functions, sorry, that we have, not operator. The methods or functions that we have. Okay, so that's the idea there. So it's going to go through and talk about some of the basic ideas here. Okay, so we have in this case, our default constructor, which is going to create an empty state. Okay, so this keeps track of the count of how many items we've created. So we're going to set our first pointer equal to null pointer and our last equal to null pointer. So we have nothing, basically. Okay. Then we're going to have the destroy list. The destroy list basically is going to go through the list and deallocate with the delete command the memory occupied by each node. Okay, so once this is done, it will set the first and last pointers equal to null pointer, and it will set the count to 0. Okay. We have initialize list, okay, which will initialize list to an empty state, and this is exactly what the constructor did. Okay, so that's what we're gonna use that code twice. Okay. Print function, which will print the data that's in each list. It'll just traverse using some other pointer. We've seen that before, where we're going to start with the current or whatever they're going to call it, and they're going to keep going until they get to the end. Okay. There's a function length. We're keeping track of count. Count's a private variable, so we're going to use the length first. The length function is basically going to be an accessor for that count variable. Okay. A couple other functions we have, since we're going to have a front and a back pointer, we can use a front and back function to return the information that's stored there. Okay, and if the list is empty, then that will stop the program. Okay, so we have a begin and an end function. Okay, and that will return an iterator. So begin returns an iterator to the first node. The function end returns an iterator to one past the last node in the list. Okay. There's the copy list, which allows us to make an identical copy of the list. Okay. So with that, we're going to create a new node called new node. We're going to copy the info into that new node, and then we're going to, that's not correct. These PowerPoints from the book side are wrong. That's the steps when we're going to create a new node to put it into the list. Okay, so that's not exactly correct. There's a destructor, there's a copy constructor. Okay. And then we've got the definition of The overloading the assignment operator, again, is going to be similar to the copy constructor, same basic idea. Okay. So then we have our class unordered list. So this is going to be the inheritance stuff again. It's going to inherit from the linked list using public inheritance. Okay. It's going to have to implement. Okay. Remember that the functions search, insert first, insert last, and delete node are all declared as pure virtual functions in linked list type, which means since we're deriving this from that abstract class, this concrete class, so we can make objects of this, means that we have an obligation to implement these functions. Okay. So this is going to be our UML class diagram of the linked list iterator. Note that we have on the right here where it's going to have the solid arrowhead here that we're connecting to or deriving from the linked list. So the linked list is the supertype or the superclass, and the unordered list is the subclass, okay, or the base and derived class, whatever terms you want to do, the parent, the child, whatever makes you happy, okay. So these are the functions that we have to implement. Okay, we've got a search, which is going to take something of whatever type, integers, doubles, circles, whatever it is. Okay, so this constant means that the type coming in doesn't change. Okay, the function itself does not change the list itself. So this constant protects the input variable since we're bringing it in. It's as a memory construct. Okay, and this protects the list itself because the search shouldn't change anything. And the return type here is Boolean. Okay, insert first, insert last, and delete node all take a type, something of type, an integer or whatever, and it doesn't change those. But note, these do not have the constant here because these all will change the list, and they're all void functions otherwise. Okay. So again, this class, the unordered list, is fully specified in the book, but I'm going to want you in class today to actually create this. Okay. So we have our function search, which is going to search through the list, the unordered list. Okay. So in this case, we're going to have to start at the beginning. We're going to have to keep looking to see if our search term is equal to info all the way until we find it. If we find it, we're done. Okay. If not, we keep moving until we're done, until there's no more data left in the list. Okay. Insert first. It's going to insert an item at the beginning of the list. So we're going to create a new node, make sure it has the data that we need. Okay. And then we're going to insert it before the first. Okay. So we're going to insert at the head of the list. Okay. Then we're going to increment the count by 1. Insert the last will be similar to insert first, but it's going to go to the end of the list and insert 1 there, and again increase count by 1. Okay. Delete node. Okay. So you're going to give it, if you have a list of integers, you want to delete 5. Okay. So you want to go and find a delete 5. If it's there, you want to delete it. Okay. A node that has that info. Okay. So you have a couple of cases to consider here. The first is that if the list is empty. Okay. If so, then just display an error message. So there's an isEmpty function you'll have to call. It could be that the node to be deleted is the first node. Okay. So if this is the case, if it's the first node that has the data that we want to delete, we're just going to have to basically reroute that first pointer and also decrement the count. Okay. If there's no other nodes, if you delete all that there is, then first and last have to be sent to the null pointer. Okay. So here's an example. We have a list of more than one node here. And if we're deleting the node with info 28, okay, we see that the first, which currently points here, has to be routed to basically first week will first link. Okay. It now points to the 17. The last doesn't change, and the count is decremented by 1. Okay. So the third case then, so case 2 was if the node to be deleted is the first one. If that's not the case, then the node to be deleted will be not the first one. Okay. So with that, we have to update the link field of the previous node. We talked about this in class before. So we're going to have to keep track of a previous node. So we're going to go through until we find the node that we want. and we're tracking a current and previous, and we'll have to make sure that we skip over that basically. Okay, and there are two sub cases here. If the node is not to be the node to be deleted is not the last one, then we do like always and just take the previous one to the next one. Okay, but if not, if the node to be deleted is the last node, then we have to update that to null pointer, which should happen anyway. But we also have to update that last pointer to previous also, okay, to make sure it still points to the correct space. Okay, so here's an example of this. We're going to delete item 37 here. So we've got it's at the first, second, third node. Okay, so once we've done that, so we're going to start here. We're going to say, is this 37? It's not. Our pointer is going to go to here. Our previous pointer will still point to 28. So now we're at current at 17, previous at 28. Is this 37? Nope. Go one more time. Current points to 37, previous points to 17. Okay. Then we're going to reroute 17 to point to 24. Okay. So just like we always do. So nothing unusual there. Here's the resulting data. Okay. So in this case, we're deleting the last element. Okay, so we've moved on. So when we get to this point again, the current will start here, it moves here, previous stays at 28, and then we're going to keep going. When we're done, current will point to 54. That'll be what we're looking for. Previous will point to 24. Okay, we'll then have to point 24, point the previous to the null pointer, and then change this last to now point to 24. Okay. And then the case 4 of so the first case was the list is empty. The second case is that what we're trying to delete is the first node. The third case is what we're trying to delete is not the first node. It had the two sub cases of whether it's the actual last item or not. Okay. And then finally, case 4 is that there's not in the list at all. Okay. With that, the list doesn't change, but we just have to let the user know that we could not find the list of the item they were trying to delete. Okay. So then we have ordered lists. That's the other thing I want you to be working on. Okay. So these have to have definitions for the abstract functions insert first, insert last, search, and delete node. Okay. But the assumption here is that the elements of the ordered list are arranged in ascending order. Okay. So this means in part that this is only possible if we have orderable items. Okay, so if we have integers, then we have no problem. That's probably examples we'll use. If we have strings, then they can be based on lexicographic order. But if you have something like a person, then you have to figure out how that equality is going to work. Okay, but all these are going to change, but we're also going to include an insert function that will actually put the element where it's supposed to be. Okay, so it's a little bit different there. Okay, so here's the UML diagram from this. And then in a bigger UML class diagram, the linked list type would now have two children, basically, the ordered and the unordered. Okay, so we have the search, the insert first, insert last, and delete node that we have to have, and we've included this just plain insert to insert it in the right location. Okay, so searching the list, as I said before, basically we're going to keep searching until the list item info is greater than or equal to what you're looking for, then you know that there's no more search. Okay, so the search for an ordered list should be quicker. Okay, inserting a node. Okay, so if we have some cases here, case 1, the list is empty and it's pretty straightforward, then we just add it at the beginning. Okay, no problems. Okay, case 2, the list is not empty and the item to be inserted is smaller than the smallest item. Then we're just inserting at the head. Okay, pretty straightforward. Okay, case 3, the item's going to be inserted somewhere else. Okay, case 3A, the new item's larger than the largest item, so it will get inserted at the end. Case 3B, it goes somewhere in the middle. We're going to have to find out where. Okay, so here shows an example on an ordered list. It's 17, 27, 38, 54. We're going to insert 65. Okay, 65. We'll go and make sure that it's not smaller than any of these. And when it gets here, we'll know to add it to the end. Okay, and the last pointer would have to be changed. Okay, now we're inserting a 27. Okay, so we start here. Okay, and that's smaller than what we want, so that's not what we want. We go here, and now we see that this is too big. So again, we're going to have a previous pointer to be able to insert the 27 in between these two. Okay, but the first and last don't change. Okay, so the functions insert first and insert last don't really work. Okay, they don't work with an ordered list. So we still have to insert the new item at the proper place. Okay, so they're not used, but we have to provide a function for them. Okay, because they're declared as abstract in the parent class. Okay, so we're going to use insert node instead. Okay, so deleting a node. So if the list is empty, it leads to an error in the same case as we had before. Case 2, the item to be deleted is the first node, and then we're just going to adjust the head node, the first pointer. Okay, item is somewhere else in the list. Okay, it's going to find it. We're going to have the current. They're using trail current where I was using previous. Doesn't matter what you call it. We have to use that one. And then if case 4, if the item's not in the list, then we're going to give an error. Okay, and that is more or less the same as the delete from before. Okay, so that's as far as we're going to get today. So hopefully you'll take a look at this video before class. If not, the things are in the book and we'll be able to get these examples up and running. Okay, so look on Moodle in addition to getting the ordered list and the unordered lists up and running from the book, there's a homework problem as well. Okay, and this will for sure take you more than class time. And I think we're getting into sufficiently complicated homework that there's going to be some homework. Sorry, sufficiently complicated programs that there are going to be some homework assignments for us. Okay, so if you have questions, make sure you let me know.